Good evening, all. Thank you so much for joining on time. And let's today continue our let us better understand motors. Let's talk about protection of motors. Protection of motors, like we can talk from multiple perspective. So we will quickly pick up ETAP, maybe one low voltage motor, one medium voltage motor. We'll pick it up and then like try to do the protection for the motors, right? When we say protection of the motors, of course we need to think about like overcurrent protection, at fault protection. If it is in the medium voltage side, this is like a relay. If it is in the low voltage side, this could be release. If it is a release, then like what are the kind of settings which we need to do? Let's do something quickly to the, let us better understand squirrel cage induction motor. More specifically, we'll talk about protection. Let's talk about maybe one medium voltage motor, one low voltage motor, right? Let's see like what are the things which we need to really look into from the motor protection perspective. And if it is release relay, what could be the challenge? Or like let's look at like a very outer surface of what are the things which we need to really take into account when we are doing the protection coordination for the motors. Let ETAP works on. In the meantime, let's look at any other specific requirements. Protection of motors, thermal withstand rotor damage curve, negative sequence withstand capability, permissible starts. Let me take a small simple example of 33 bar 6.6 kV. Let's consider maybe 6.6 kV medium voltage motor. HV side, I'm taking 33 kV. Assume this is an industry. Receives the power supply from utility. 25/31.5 MVA transformer. Typical impedance. Like I will come to this grounding part little later. That's help us for earth fault detection. And let's assume 33 kV, like the fault current is about maybe 15 kiloamps or 10 kiloamps. Let's take 15, expire is 14, and we are done. And let's now take one transformer which step down to 400 volt. And like let's connect maybe two motors at the LV and at least one motor at the HV and try to find out. Let's take maybe 2 MVA transformer. So let's probably pick up two motors, one motor with LSIG release, another motor maybe with thermal magnetic release. Let's look at like what could be the difference and what are the challenges which we can face. We can go to that, and then we will come down to a medium voltage motor as well. Like of course, because of the interest of the time, I'm not really modeling the cables and stuffs, but definitely we'll put up CT and relay, right? So this is the protection which we are going to talk about. So let's pick it up. Some capacity motors. What's the capacity of the motor which you want to have a protection for? 400 volt, you have two motors, 6.6 kV, there is one motor which is available. All right, 750 kilowatt is the answer. And I will be coming to little later, like what are the other additional informations which we need. Then let's pick 140 also. Yep, probably if you want to protect maybe some other capacity motor in the low voltage, still option is open. So let's probably go to this motor and open up a Word file. When we are talking about motor protection, what are the specific information which we need to ask for motor protection? Like I am trying to protect the motor and I am trying to protect the motor with overcurrent and earth fault. In order to set overcurrent and earth fault, what are the informations which I need from the motor? I'm not really asking about the network, I'm asking about the motor. What are the informations which we need to ask for a motor to protect that motor? Of course, a data sheet. In data sheet, like more specifically what parameter. If time allows, please show how to show VFD characteristics in TCC curve for MV motor. Even though no importance of VFD in TCC, client is asking. Really an important question. VFD has a characteristics really significant when it comes to protection. Of course, we need to ask motor rating in kilowatt, voltage in kV, power factor, efficiency. These are the informations by default we need. And we need to ask what is the lock rotor current. We need to ask what is the lock rotor power factor. We need to ask what's the starting time of motor at 100% voltage. Minimum possible percentage voltage, I am giving straight away 80. It is not necessarily has to be 80, it could be 75, it could be 70, it could be 85, it could be 90. What's the minimum voltage at which the motor starts? That's starting time. And of course, what's the maximum permissible voltage which is allowed? So motor starting time. Motor hot withstand time. Like these are the informations which we generally need. But like another important aspect, needless to say, something which we need to ask is what is the time versus current characteristics of motor when it is started with the help of starter. Why do we need to probably means for say showcase VFD? We are not really showcasing VFD, but like when VFD is used as a starting device, how the starting characteristics changes and what needs to come to the graph. That's what we'll probably pick it up. So now probably if I have put it in Excel, like I can fill this parameter straight away, or probably means here also you can write it. Rating 140 kilowatt, voltage 0.4 kV, power factor do not know. Let's look at what's the power factor of that motor. 0.9168. Efficiency 0.9271. Lock rotor current 6 times. Lock rotor power factor 0.2478. Right. And then like we need to ask really some important informations. What's the starting time at 100% voltage, 80% voltage, and 110% voltage? And important informations to ask, like I'm just giving 4, 6, and 3 seconds. 100% voltage 4 seconds, 80% voltage 6 seconds, and maybe 110% voltage 3 seconds. All the informations are given. Motor hot withstand, and that important information which you need to give. Like let me say it's 15. All done. All the informations needed for the motor protection. When I say motor protection, it's overcurrent and earthfall protection. We are done. And let's go there. We are done. Let's pick up this circuit breaker, relay, release, whatever it is. Like in this case, it is circuit breaker with the release. 140 kilowatt motor. Right. Now we got something. Motor at 100% voltage. That's the red curve. Probably we can increase the thickness. Keep it maybe dark red. That's 100%. Yep. And we can probably have other options too at 80% voltage, and just trying to differentiate this in a different color. Yep, and I am done. So means I have got 140 kilowatt motor, 400 volt. Power factor is known. efficiency is known, locked rotor current is known, locked rotor power factor is known, starting time at 100% voltage is known, which is 4 seconds. Starting current at 110% voltage is also known, that is 3 seconds. Starting time at 80% voltage, which is also known, which is like 6 seconds. So automatically this characteristics is developed by the motor. And of course, one interesting fact, if you are not really aware what is that asymmetrical factor, if we consider asymmetrical factor, as 1, this is a straight line, but during starting, motor will not draw really a sinusoidal current. During starting, when I'm closing breaker, like all the 3 phases get closed. R phase closes at a different instant, Y phase closes at a different instant, D phase closes at a different instant. And the current during the starting will not be like pure sinusoidal. It consists of some asymmetrical quantity. And if you assume asymmetrical factor as 1.6, like this is the curve which we are seeing. And probably means if you're considering it's maybe like 2, you can get like further the graph goes something like this. Right, like this is another important aspect. In absence of data, like you can assume 1.6 as an asymmetrical factor. That's really a good number too. So motor for liquid booster pump, 140 kilowatt, 400 volt, 50 hertz, like almost all the data which we have probably, I guess, like we can probably pick it up. Rated current is 249 amps. Startup current is 7.8 per unit plus 20%. Starting current is not small. Starting current you can look at like 7.8 times plus 20%. Cooling time constant. But like we are looked at some other interesting factors which is not really known. Minimum voltage at terminals to start 80% voltage, that's great. But like we have looked at other details in this data sheet which is not really available. So rating, voltage, these 2 informations are available. Lock rotor is available there, this data sheet. Let's look at like, is there any other data which is available? I didn't really find anything else. 249 amps current we have found, like from there, like we need to derive power factor and efficiency, which might be difficult. Yeah. Specific startup time, 100% and 80% voltage, that data is there, 1.5 seconds and 2.5 seconds, which means like we can update this numbers. All right. So, but like current rating, give an idea like whether what's the data which we have considered is okay or not. Float current is 237 amps, 140 kilowatt, 400 volt. Here rated current is 249 amps, which means like power factor and efficiency is still poor, but like unless otherwise we get the data, right? Like we have a data here. Power factor is 87%, like 2/4, that is 50% of the load, 3/4, that is 75% of the load, 4/4, like that is typically like 100% of the load you have a data. 93% efficiency, 87% power factor, which we can feed this data. 87% power factor, 93% efficiency, 249.7 amps. That's perfectly all right. And like the 75% data, if you want, you can fill it. 93, 84, 93, 50%, 91, 77. And during no load, data is not given. Lock rotor, the power factor is 0.38. That is like starting power factor is 38%. So we got like some good informations. Lock rotor, like power factor is 0.38, which we got. Here, like we got 7.8 times plus 20%. I guess like which we need to really update it in ETAP. here what we need to do is 7.8 into 20% margin. So that's the value which we need to probably put it. 9.36, that's 936 is the current. And now if I give this information, probably means, let's say, you can see there is a drastic shift in this all the graphs. That's obvious, but like one more information which we failed to update is like it is 1.5 and 2.5. So here like there is no data, right? Like this is actual motor characteristics with all the informations from this image. Now if I am setting up overcurrent protection 51 and 50, I need to ideally probably put this curve above this starting characteristics and below this damage characteristics. And like this data is as such, I couldn't really find it. Like we have assumed hot withstand capability is 15 seconds. We need to check that. Is there anywhere it is mentioned? Heating time constant is completely different. That's not how much time this motor can withstand during lock rotor conditions. I don't think that information is available. Lock rotor time, yep, we have lock rotor current, right? I'm not sure like whether it is visible or not. So 8 seconds, let's take like 8 seconds and check or test this, how this curve becomes. Now it's our responsibility to put up the breaker characteristics in such a way that it is above the release details, above the starting characteristics and well below the withstand characteristics. So we know what is the full load amps, 249. So let's take maybe 400 amps breaker. One side on thermal magnetic, let's pick up thermal magnetic itself. Beautiful. So if I have picked up thermal magnetic, it gives me a very clear and straightforward message. This is my starting characteristics, and most of the time during starting my release will pick up. That's because the motor starting current is like 9.36 times like 7.8 plus 20% margin. So literally if you have like 7.8 times the starting current and the full load current is like 249 amps, then literally choosing the breaker rating of 400 amps is a suicide attempt. Is kind of a suicide attempt. Right? Let's try to have the maximum value which is possible, like which we have done. Still you can see here like there is an overlap. Let's make it 100. Even there is an overlap, right? So this gives a very precise and clear cut message. If you have this motor, if you have motor with this characteristics, this cannot be protected effectively by your thermal magnetic release. Even if you go with 400 amps thermal magnetic release, sometimes this will trip during starting. That's message, I guess, like it's pretty much clear from this region. It trips, and like this is also very clear from this image. There might be a chance that the motor may not be completely protected. If it operates somewhere here, then the motor might get damage also. So it's neither preventing maloperation of the relay during the starting, nor protects the motor effectively, right? Like that's the drawback of thermal magnetic release. And let's pick it up the same thing, and probably means what to say. Let me look at another aspect of it. Let's have LSIG release. Let's take all the details since we have given all the details. Let's copy this and let's try to have a release, and that release is electronic, and it could be like further higher sophisticated adjustable. Let's try that. Let's maybe pick some other different manufacturer. NSX 400, Micrologic 6.3. I have picked up 400 amps, Micrologic 6.3A, right? So we have probably picked up a release, which is electronic release, protecting the motor, adjustable. Now let's take this motor and this to the graph and probably compare how this protects the motor, right? Like in order to have a comparison of both the breakers in the same graph, I'm just trying to append this circuit breaker, right? Like here you can see this is the circuit breaker. Let's see how electronic release is far better from multiple perspectives. Yeah, I guess like more or less it's making some sense. The different color release, what you are seeing here is thermal magnetic, and probably let me bring this to the front and say it in probably a different color, right? So you can see the difference between thermal magnetic release and electronic release. Don't read that as like ABB versus Snyder, right? It's like thermal magnetic versus electronic. So here, like with the thermal magnetic, you neither prevent the maloperation during the starting nor protect the motor against the damage. But with the electronic release, you have prevented the nuisance tripping against starting the motor. You have also protected the motor probably properly, right? I guess like still there is a room where you can further fine tune your settings, but like motor is comparatively well protected. If you got the difference between advantage of electronic release versus thermal magnetic release, decide this release when you are probably ordering the switch gear. And when you're ordering the switch gear, you may not have this data sheet, but this data sheet will be available to the person engineer only after placing the purchase order on the motor. When we place the purchase order on the motor, and when we are probably getting the means of the data sheet from the OEMs, by the time we would have ordered the LV switchgear also. But we need to know this details, and then probably we need to probably coordinate and check the release setting and properly order this particular release what you need. That may not be always possible. That's because you may not have all the informations what you need, and you will not do the relay coordination till probably you get all the informations from the motor manufacturer and particular release model. And when you have a cable schedule, when you have a motor data, when you have a transformer data, when you have a short circuit report approved, when you are approaching the relay coordination, you might have already ordered the release, because only with the release you will be able to do the relay coordination, release details, make, model number. Instead of Snyder, if you are going for an ABB, the release details will be different. If you are going for somebody else, the release details will be different. So by the time when you have all this, and then probably if you found, oh my goodness, it's only thermal magnetic release, whatever I try, the adjustable capability of the pickup is from 70 to 100 in steps of 6%, and like magnetic trip is like 5 to 10 times, but unfortunately that is not protecting my motor. If you understand, probably when you are doing a relay coordination, you cannot change the release or a motor, because that's already ordered. It's means was already manufactured, manufacturing clearance is given, and this might be arriving at site, or this might have already reached the site. And after everything has reached to site, changing this release or changing the motor, I don't think it's practically possible. technically it may be possible, but commercially it is definitely not feasible for EPC contractors. So we should have a clear thought, like whether we are ready to compromise on the protection and go for a thermal magnetic release, or like we can go with electronic release, though that is expensive, right? Of course, electronic release is an expensive affair for EPC contractors, and they never care, because like at the end of the day, they have to just complete the project at the minimum possible cost. So if you're sitting as an engineer there, like you need to take a call, like what could be compromised and what not at the beginning of the project itself. When I have probably put up a graph, I have drawn this motor starting characteristics like this. But the starting characteristics is applicable for direct online starter, not for the soft starter, not for a variable frequency drive. If you have a soft starter or a variable frequency drive, then how to draw this characteristics? This is a starting characteristics of this given motor with the direct online start. If the same 140 kilowatt motor is started with a VFD or it is started with a soft starter, the starting characteristics will not be the same, because it's not going to draw 9.6 times the current. Instead, it is going to draw only 3 times the current or 4 times the current. But the motor will not start in 1.5 seconds or 2.5 seconds. It may be going to start at like 15 seconds or 20 seconds. So how the scenario will change, just to bring that, and probably means to say compare, that's a curve which you need to get it from dynamic motor starting study. But just to give an idea, I'm just changing this data. So now, like you are seeing two different stuffs, right? One is for a motor that's started with the soft starter, and other one is another motor that is started in direct online. So motor M1 is, whereas M4 is a soft starter, and soft starter I got some characteristics, like I have assumed that like the motor will take about 15 seconds to start, because like slowly like we are changing the voltage, but I have reduced the starting current from like 9.3 times to just 3.5 times, and that's the reason why like the starting time has increased. But now that, like selling directly something like this is not really right. So this characteristics like has to be, looks like this. The characteristics of the motor has to be like a red line versus this withstand characteristics, but unfortunately has changed to this, where there is an overlap on the withstand capability and the starting time itself. That's because it's quite natural, like means hot withstand time is like only 8 seconds, which I have considered, whereas motor starting time is like 15 seconds. That's the reason why there is no overlap. But both are technically right. Motor is taking 15 seconds to start, but it is taking 15 seconds to start in a soft starter. So what essentially you need to do, you need to perform a dynamic motor starting study. You need to model the motor, you need to model the starter, you need to model the load, you need to give the inertia properly, do the dynamic motor starting. When you do the dynamic motor starting, you will get a starting current versus time characteristics. And the starting time versus current characteristics, you may not know how it looks like. And essentially, that is precisely what you need to draw instead of this characteristics. If you're using any starter, that could be like LRS starter, that could be a star delta starter, that could be a soft starter, that could be using VFD, right? You can use any starter, FCMA starter, you can use any starter. If you're using a starter, you need to know, what is the starting characteristics of the motor, and that starting characteristics of the motor has to be properly configured, and that probably you need to draw as a user curve. So when you open it user curve, this is not practically possible. So what you need to do, you need to do dynamic motor starting study and get the VA characteristics, not VA characteristics, time versus current characteristics of the motor during starting, and that you bring it as a curve here by means of curve point 1 and 2. Like if you give that Excel import, like means was say you perform a dynamic motor starting study in the graph, you export that to Excel, and then probably you bring that as a here, then probably you will get a curve. That curve might be different. That curve might be something like this, because the starting current will be less. Starting current will be less, maybe 3 times or whatever it is less, but it may take some time like this. Right, like this could be the starting characteristics. What is the red line which I have marked now? That could be the starting characteristics. But when you are doing a relay setting, it is important you need to perform a dynamic motor starting study. If the starter is different, and that characteristics you need to bring it here, and then probably you need to coordinate the relay. And soft starter or a variable frequency drive may have bypass option. Then probably means like the motor can start in direct online. So draw the time versus current characteristics with the soft starter. With the DOL, you need to set your relays well above this, right? Like it is starting time, and probably here your curve has to come like this. So the blue could be your protection setting, and like it is extremely challenged to probably set your motor when the motor is started with the help of LRS starter or FCMA starter or a soft starter or a variable frequency drive. Variable frequency drive will not withstand the through fault. Maybe like maximum it will withstand like 2 times the current, maybe for like 3 seconds or something, right? Like we need to probably check what is the withstand capability of the variable frequency drive. You need not really put variable frequency drive capability in the graph, but what you need to essentially put is you need to add a new other user defined curve, that is the time versus current curve, which has to be brought into the TCC curve with what's the starting method which is adopted, and this curve you will get it in dynamic motor starting study. This is true except DOL. Only for a DOL starter, you can rely on what's the data which is coming from ETAP. For all other starters, variable frequency drive, soft starter, FCMA, like all other starters, you need to perform dynamic motor starting. Worst case, what is the starting characteristics of the motor, that you have to bring it manually into the graph, and you need to set the relays above this. Otherwise, this will be either causing malapprehension during the starting, or this will probably, I mean, what to say, may not protect the motor when there is a fault in the motor. Like we have quite a lot of examples. One of the projects in Qatar, during energization, the motor has tripped only 30 times. Means was the customer has adjusted the setting, probably some other consultant has given, like he has probably modified the setting at site, like, and he has tried it again, and probably means after 30 attempts, then he has understood it is not the trial and error, it's a science. So then like he came to us and we have provided a solution. The important question what you need to ask is, what is the motor time current characteristics with the help of the starter which you are using. Only for a direct online, you will get it directly in ETAP, but other starters, you need to perform dynamic motor starting study and get the time versus current characteristics. What is to be considered additional in case of motor feeding by a contactor? Nothing else. Contactor plus fuse might be the case, as those like nothing else. No other additional thing which you need to consider. But of course, the fuse should not really mal-operate during the starting of the motor. That's the only thing which you need to ensure. So the rule is quite simple. You should not mal-operate during the starting. And when there is a fault, the motor should not get damaged. Before that, your protection device has to operate. Like these are the only 2 things. Breaking of a contactor will not really break the fault current. So means when you have a contactor, definitely you have to go for a fuse. So means say overcurrent protection is, or overload protection is provided by your contactor, 49 and 51. But 50, you will disable it in that particular relay, and 50 is basically taken by a fuse. Even if you enable 50, probably the fuse will operate in 3-4 milliseconds, which is definitely will not allow, or it will not wait for the relay to respond for a fault. All right, in case of resistive earth fault, like one of the other topic which we have not really discussed today is like all about the earth fault. Earth fault depends upon the what's the minimum earth fault current available. So means what say when you are doing the motor starting, and probably means what say using probably the softwares like PSCAD, you will get like what is the unbalanced current during the starting, unbalanced current and unbalanced time, everything you will get it. When you're setting an earth fault setting, you need to ensure that whatever the unbalance which happens during the normal motor start, the relay should not malaoperate. The relay should not malaoperate for the unbalances during the starting of the motor. So getting that curve is like again further difficult, because even if you perform a dynamic motor starting study in ETAP assumes your R phase, Y phase, B phase currents are equal during motor starting. In reality, it is not so. So there will be an unbalance that has to be captured only in softwares like PSCAD, not really in ETAP. So which means like if you want to really fine tune your earth fault setting, then probably means what you need to do, you need to go to study the unbalance of the motor current during the starting using PSCAD. From that, get the worst case unbalance and time plotted, and above that you set it in time means to say SF51 setting. But like literally it is technically impossible and it is time consuming. So typically 10% of the pickup having a normal inverse with a time dial of 0.1 will not have any nuisance tripping during starting of the motor, unless otherwise the motor has some peculiar characteristics or whatever it is. So what I mean, 10% pickup, normal inverse with a time dial 0.1 will save the motor for the earth fault. It will not really cause any nuisance tripping during the start. And that's precisely what this graph has covered. What I need is I need a current versus time characteristics of the motor in the starting. This is ideally I need, and like I cannot really get that from the variable frequency drive manufacturer, because this depends upon variable frequency drive settings and then probably the motor characteristics and along with what's the load which you have connected, right? So that has to be an outcome of dynamic motor starting study. That's where it gets challenged, and probably means to say doing a dynamic motor starting study itself probably becomes another important task for such protection. This one, but like there is no other go. If you want to protect your motor carefully, like that's essentially which you need to do. You have multiple options in synchronous motors. Assume that I have a synchronous motor in our case instead of an induction machine. You can talk about like what mode it has to operate, right? So you say example, if I'm putting like 2 megawatt motor at 6.6 kV, it can operate it in different modes. When I say different modes, like MVR control or power factor control or whatever it is. So if you're putting it in power factor control and put it power factor as unity, this will not really consume any reactive power. So whenever you have a synchronous machine, means to say you can probably means to say give unity power factor, which slightly stress your excitation system higher, and that temperatures more, because like means you need to have higher field current to come to this normal excitation system. But like if you're having it instead of like setting 0.98 power factor lag, this has an advantage that it will not draw any reactive power from the source. That's pretty much like what we need to really look into when it comes to the synchronous machines, right? Synchronous machines generally used for a large capacity, not for small or medium capacity. And when you're given the large capacity and predominant load of your industry will be of like synchronous motor, and hence like you need to take care of the power factor. And if you are not taking care of the power factor of the synchronous motor, then probably it have an impact on the net power factor also. you can use your synchronous machine in an overexcited conditions to inject reactive power, but that means that will go to the overexcitation condition, and that will further increase the heat of your rotor. And if you want to get some reactive power from the synchronous machine, like for an applications kind of synchronous condenser, you can very well use it. So I mean, so a synchronous motor has the capability to inject reactive power, consume reactive power. So I generally prefer like neither inject nor consume reactive power. But if the situation needs for the power factor correction to inject reactive power, which you can very well inject the reactive power. So if you are operating always in lower excitation, then motor heating limit, rotor heating limit more specifically is what you need to really look into. Thank you all. Thank you so much. Have a great day.